we are going to do is a step-by-step derivation of the 95% confident interval. First, we need some tools. So the first tool is expectation is linear. Suppose I have two random variables x and y, and the expected value of x is mu x, expected value of y is mu y. Then what's the expected value of ax plus by plus c? It will be a mu x plus b mu y plus c. Okay. So the second thing is quadratic formula for variance. So suppose I have a random variable x and y. The variance of x is sigma square x. The variance of y is sigma square y. What's the variance of ax plus by plus c? If x, y are independent, it will be a square sigma x square plus b square sigma y square. So the third thing is about normal random variable. Suppose x is normally distributed with mu and sigma square. Then by 1, if I add c on x, that means I shift everything in x by c amount. Then this shifting will affect the mean by mu plus c, but it does not affect the variance. So x plus c will be also a normal distributed random variable, but it only shifts the mean by plus c. Then suppose x is the same random variable. Because of 1 and 2, if I scale x by constant c, then the mean of x will be scaled up by the c, and then by 2, the variance of x will be scaled up by c squared. So cx will be a normal distributed random variable with mean mu c and also sigma square c squared. IID. So suppose I have two random variables x and y. If they are IID, then that means the joint probability of x is x, y is y can be split into the product of probability x is x and y is y. Okay? And suppose I have a bunch of random variables x1, x2, x3 up to xn. They are all IID. That means this joint probability, that means the probability of this n event exists at the same time, can be split into a product of n marginal probability. Standard random variable. Suppose I have an x that is normally distributed with mu and sigma square. Now, suppose I consider subtracting the x by mu amount. What happened? I shift my mean by negative mu. So mu minus mu, it will give you 0. Then I scale the whole thing by 1 over sigma. If I scale with this, it's like I multiply the random variable with a c. And here, my mean is already 0. So multiplying c with 0 gives me still 0. But the c here is 1 over sigma. So it will divide sigma square by sigma square. So it gives me 1. So this random variable with 0 mean variance 1 is called standard score. And we call it z. So now with 1, 2, 3, 4, 5, we are ready to derive confident interval. So suppose we are given n values, x1, x2 up to xn, okay? So sample mean is basically the average of this n value. So x1 up to xn, take the sum, divide by n. So we are going to assume on this x, they are IID. That means we will have this, okay? We will have 4. And we assume all these random variables are normal distributed. And our goal here is to find what is the average of this x bar and what is the variance of this x bar. So we are going to show that if all the xi in these n values are all normal random variable with the same mu and the same sigma square, then this average will also be a normal random variable with the same mu, but the variance will be divided by n. So let's study the proof. First, x bar is x1 plus x2 up to xn, and then divide by n. I split the sum into individual terms. If xi is normally distributed with mu and sigma square, then scaling it with 1 over n will give us a normal distributed random variable with the mu divided by n and sigma square divided by n square. This is because of 3. If x is a normally distributed random variable, then scaling with a constant cx, we will scale the mean, also scale the variance by c square. Now c is 1 over n, so it will give us mu divided by n, and c square is 1 over n square. So we have this. Now we are going to talk about the expected value of x bar. Will be expected value of this sum. Since expectation is linear, so I can distribute the expected value into each of these terms. And this 1 over n are constant, so I can take it out. So that means expected value of x bar will be something like this. And now, because all the x are IID, this is by assumption. Xi are all IID, and they are all normal random variables. So all their expected value is mu. So we will have a bunch of mu divided by n. How many of them? There are n of them. So therefore, taking the sum, it will give us mu. We have shown that the expected value of x bar will be mu. And what is this? This is this part. The expected value of x bar will be mu. Then what's next? We are going to prove that the variance of x bar is sigma squared divided by n. The variance of x bar by definition is this thing takes the variance. By the quadratic formula of variance, we can distribute the v into each of the x terms, and then for all the 1 over n, we will take a square. So it will be 1 over n squared times the variance of x1 plus 1 over n squared times the variance of x2, and so on until 1 over n squared times the variance of xn. And since all the x are IID distributed and their variance is sigma square, so all the Vx can be replaced by sigma square, sigma square. So we have a sum of n sigma square divided by n square. And since there are n terms, so we will get n times this thing, and cancel out the n, we get this. So we have shown that the variance of x bar is sigma square divided by n. So now we said that given n values x1, x2 up to xn, if they are all identically and independently distributed, that they are all normal random variable, expected value mu and variance sigma square, then the sample mean x bar, which is the average of this n random variable, will be also a normal random variable, that is having the same expected value mu, but the variance will be divided by n. So what's next? We are going to combine 5 and 6. So recall that if I have a random variable x that is normal random variable with mu and sigma square as a parameter, then if I perform the operation x minus the expected value mu and divide by the standard deviation, that is a square root of variance, this random variable will be a standard score, that is a normal random variable with zero mean and variance 1. Now I'm going to do this on this x bar. So if x bar is normal random variable with parameter mu and sigma square divided by n, first I subtract x bar by the mu here, and then divide by the square root of this thing, like this, which is this, then we will have this whole thing will be a standard score. This whole thing be z. Probability of a z variable bounded between a and b will be like this. The probability density function take integration from a to b. So if x is a Gaussian random variable, then the probability density function will be 1 over square root of 2 pi sigma square multiply the e power x minus mu whole thing square divided by 2 sigma square. We are considering standard score. That means 0 mean and variance 1. So we plug in, so we get this expression. So that means the probability density function of x, given that it's 0 mean variance 1, is just 1 over square root 2 pi e to the power negative x square over 2. So that means the probability of random variable z between a and b will be this integral. We said that in the very beginning, we consider 95% confidence interval. That means the probability is equal to 95%. This integration gives us the value 0.95. This is saying that if I consider this function as a bell curve, if I integrate from a to b, the area under it should give me 0.95. I can use this to find the value of a and b. And this is an even function or a symmetric function. That means I can do this. So instead of integration from a to b, I can integrate from 0 to b and then 2, assuming a and b are symmetric values. So solving this thing, which I can move everything to the other side, give me this expression. This is the integration that you don't know how to solve. That's fine. I will give you the answer. B is 1.96. So that means the probability of the z variable between negative 1.96 and positive 1.96 is 0.95. So z is x power minus mu divided by sigma under square root n. So we are going to rewrite the thing inside to make mu in the center. So what I'm doing here is that I multiply the whole expression here by sigma divided by square root n. So it gives me this. From here, I multiply negative 1 in the whole expression. Basically, I flip the sign of the whole expression. I get this expression. So from here, I just add the whole expression x bar. So I get this expression. So what does it mean? It means mu is within an interval. Mu, this unknown, is within this interval. What is this interval? This interval is built on the sample mean. That means we are using the estimation from the data and then subtract 1.96 times the variance divided by the square root n. So this is like the uncertainty from the data. We are using this uncertainty of the data to expand our x bar to give us an interval. And this interval is called a 95% confidence interval. Mu will be within this interval with 95% confidence. So this is how you derive the 95% confidence interval. So therefore, what is 95% confidence interval? We are given x1, x2, xn as n values. Then what? We compute x bar as the average. And then we compute variance, and then mu, the expected value, will be within this with 95% confidence.